we were discussing, and this is a very important lecture also today, considering that we are trying to integrate the existing high performance computing mechanisms along with the quantum mechanism. So just like how, if you are aware of general processing units, you can't run the GPUs alone without the CPU. So in a sense that we will not be able to fully run a quantum system. So we will need the high performance computing to support whatever we are doing. So, or we take both of them together as a hybrid combination. So it should come a little later, but because of some slight adjustments that is coming earlier. So we will try to listen to how we will integrate the CUDA quantum, that is CUDA Q. CUDA is Compute Unified Device Architecture, which is basically used for running codes on GPU, that is NVIDIA GPUs. So you use the programming language called CUDA, CUDA, and now we look at CUDA Q, which is a quantum approach, again coming from NVIDIA. And as we see, NVIDIA is also investing a lot in quantum approaches. Many companies, in fact, yesterday I was talking to MATLAB, he was also mentioning that they have some approach to quantum. So everybody is looking at how do I include quantum in my this thing. So Mr. Anand Raman today will be sharing with us on how to do that. And he's coming with a lot of experience, more than 9.5 years of experience in NICER, handling high performance computing systems. So that is where the experience is there, and he's working as a scientific officer in National Institute of Science, Education and Research, Bhubaneswar, and he's been there for more than around 10 years. And he did his master's degree from Kalasalingam University. But more important is his experience with running these high performance computing systems. And in that sense, he's very much qualified to take this. And he has taken this lecture in the previous courses as well, especially related to high performance computing. So without much delay, let us look at the session by Mr. A. Anandaraman. Thank you, sir. Thank you for joining.
Thank you, sir. Thank you. Is my slides visible, sir?
Yes, sir. Yes, sir. Slides are
okay. Okay. Yeah. So good morning, good afternoon to all. Yeah. So today we will see about how to integrate HPC with quantum computing. Okay. There are a lot of tools coming up. So one among that is CUDA Q. So by NVIDIA. So Qiskit and other tools, everything is there. So yeah, each has some advantage, some disadvantage. So everybody's coming for this integration. So better to be aware of all those things. So like Qiskit, Google CIRQ, so CUDA Q, NVIDIA's CUDA Q. So there are so many platforms. So we should be aware of each and everything at least. Then we can choose the right path, and we don't know whose approach will be giving more results. So better to learn everything at least to some extent, and then we can stick to some of the single concept. And yeah, so today we will discuss about what is HPC, what is background of HPC, why HPC is needed, and how GPU is coming into HPC for accelerating HPC. Okay, accelerated supercomputing. And then we will discuss about this quantum computing and how accelerated quantum computing. So it's like, so accelerated quantum accelerated supercomputing. Okay. So how this supercomputing or HPC is getting accelerated by GPU. Now in future it will be accelerated by quantum processing unit, QPU. Okay. And some programming tools, that is CUDA Q, and we will see the demo sessions. Yeah, so little bit introduction about scientific computing. So what is research? Research is we need to observe something, and based on the observation we have to create a hypothesis, and to validate the hypothesis we have to do the experiment. Okay, if we get the result, then we will stop it. Otherwise, again we have to observe from the mistake, and again we have to redesign the hypothesis, and again you have to do the experiment. till you get the right result, this process, this cycle will follow. Okay, observation, hypothesis, experiment. But if you do observation, hypothesis, and experiment, so there are a lot of cost involved, time involved. Okay, so for every prototype you have to spend money. Okay, and for everything, time is also getting wasted. Okay, so they introduced the fourth paradigm, that is called computation. So observation, hypothesis, computation. Again, you repeat this loop. When you get the near result in computation, then you do only that experiment. Instead of doing all the iteration experiment, you do okay whatever in computation. Okay, if somewhat okay near result, because computation always have some rounding of errors. So if some near approach, near solution is coming, okay, that approach you can try in the experiment, so that the number of iterations in the experiment getting reduced. So this is the basic research cycle. So computation is the fourth paradigm of science. Okay. So what we are going to do simulation. Okay, so what we are going to simulate, we are going to simulate the physical system only, because physical system, it is very hard to simulate it. So we have to understand the physical system, and we have to make it as a mathematical model. Okay, converting physical system to the mathematical model involves these conservative laws like heat and heat equations. Okay, those equations, conservative laws, and constitute relationship between those things. Okay, for your prototype, what is the relationship? So with that, you are converting the physical system into a mathematical system, and then that mathematical system should be solved using computer. Usually this mathematics, okay, when you convert the physical system into a mathematical problem, okay, that problem actually falls in partial differential equation. Okay, but partial differential equation cannot be directly solved by digital computer. It can be solved by analog computer, but it cannot be solved by digital computer. So in order to solve the partial differential equation, so we are again converting into a algebraic equation. Okay, so partial differential equation must be translated into algebraic equation for computational solution. So if algebraic equation can be solved using digital computer, so this is the process. So first we are taking the physical system, we are converting into a mathematical problem. That mathematical problem is in the form of partial differential equation, mostly, not all, mostly it is partial differential equation. Since partial differential equations cannot be solved by digital computer, okay, so we are converting it into a set of algebraic equation, and then we are solving it. That is linear algebra. Okay, so for HPC and quantum, linear algebra is very very important. Okay, so without linear algebra we can't do anything, because we are getting partial differential equation. If you model the physical system into a mathematical model, as a result we are getting partial differential equations. Since partial differential equations cannot be solved directly by digital computer, we are converting the partial differential equations into set of algebraic equation. Okay, then the algebraic equation is getting solved by computer. Okay. Okay, so when we are solving those things, okay, we need some set of requirements. The computer should be capable of doing this many calculations per seconds. Okay, then only we can do. So what is that? Whether it is integer type of calculation or it is a floating type of calculation. Since we are dealing with scientific things, our accuracy is very important. So we cannot deal with integers, we cannot round it off any numbers. Okay, whatever the value we are getting, we have to preserve it at most, so that we will get the accurate result. We cannot round it off. So real world problems are continuous. There is these are not inherently integer values, they are not integer values, so we need accuracy. Okay, so precision and range. So precision, floating point number are designed for this. Okay, so floating point number, so followed by fraction, after that you can have multiple digits. Okay, so range is also important. So Planck's constant and atomic distance, so they are large, and speed of light. So very small number also you can represent with floating point number. Very large number also you can represent with the floating point number. So So the computer which is being used for solving this algebraic equation should be capable of doing more floating point operations per second. So that is the benchmark. Okay. So okay, if anybody asks, okay, what is your HPC size? So we can say, okay, it is 100 teraflops. Tera is 10 power 12. So 100 into 10 power 12 floating point operations per second my computer can do. So that is how they tell. Okay. So yeah. So basics for global ranking. So here top 500.org list is there. So this list is based on the floating point operations per second. Okay, that computer can do how much floating point operations per second. So we need to know how the floating point operations per second is calculated. Okay, so floating point operation, okay, it has different formats. So double precision, single precision, half precision, quarter precision. So for example, you need 64 bit to represent one floating point operation, one floating point number. Okay, then it is called double precision. If you represent the same number with 32 bit, then it is single precision. If you represent the same number, floating point number, with 16 bit, then it is called half precision. If you represent with 8 bit, then it is called quarter precision. Okay, so for 64 bit, 32 bit and 16 bit, IEEE standards have been established. But for quarter precision, it is introduced by NVIDIA. So but still IEEE is not established, IEEE format is not established. Okay. So this is how floating point operations per second is calculated. So this is the formula. So teraflop is equal to number of cores into what is the processor clock frequency. This is the base clock frequency and the flops per cycle per core divided by 10 power 12. That is because of we are getting teraflops. Okay. So here each processing element has a FMA, okay, fused multiplication adder. Okay, this is actually it's a one instruction, but it can do two operations. So it can do one multiplication and one addition in one instruction. That is called fused multiplication adder. Okay. For example, A, B, C are the inputs for FMA, fused multiplication adder. Then it will do A into B plus C. So this single in a single instruction, this two operation is carried out. With one rounding, each core has two FMA units. So we have computers with several cores. Okay, so if your computer has 4 core, each core has two FMA units. So that means totally you have 8 FMA units for 4 cores. So like that, okay, for each processor we have to calculate. So floating points operations per second per cycle per core is equal to number of fused multiplication adder units into flops per FMA per lane into lane per vector. For example, each FMA does two floating point operations per lane. Okay, so one multiplication and one addition it does. Each core has two FMA. That means each core can do 4 operations simultaneously. Learn per vector. Okay, what type of so whether you want to do double precision, single precision, half precision or quarter precision, that is a vector width. Okay, so divide by element size in bits. So if it is SSC, it is 128 bit. AVX is the advanced vector extension 2, it is 256 bit. AVX 512 is 512 bit. Okay, so here we are just considering floating point 64. This is called 64 means it is double precision. That means one floating point number is represented as 64 bit. Okay, yeah. So it's equal to so it's two lanes. So if it is 32 bit, then it can handle 4 lanes because 128 has how many 64? It has 264 bits. That means two floating point 64, that is double precision operation you can do. If it is AVX2, it is 256 bit. Okay, then you can do 4 floating point operations double precision. If it is single precision, you can do 8. Okay. Similarly, if it is AVX 512, so there are 512 bits, so you can represent 64 into 8. It's 512. So you can have 8 double precision floating point operation or 16 single precision floating point operation. Okay. So this is why HPC is needed. For example, weather forecasting. Okay. So atmosphere modeled by dividing it into three-dimensional cells. So atmosphere, total atmosphere, Earth atmosphere is divided into three-dimensional cells. Okay. Here each one is cell. Calculation for each cell repeated many times to model passage of time. So at time t1, we will do the calculation for one cell, t plus 1, t plus 2, t plus 1. So for each time, we will do some set of calculation for each cell. Okay. Suppose a whole atmosphere 5 into 10 power 8 square mile divided into cell of size 1 mile into 1 mile into 1 mile to a height of 10 mile. Okay, 10 cell height is equal to 50 into 10 power 8 cells. So totally we are getting 50 into 10 power 8 cells. Okay. Suppose the whole atmosphere 50 into 10 power 8 square miles divided into cells. So we are getting 50 into 10 power 8 cells. Okay. So each calculation required 200 floating point operations per second. In one time step, we need 10 power 13 floating point operations per second. Okay. To forecast the weather over 7 days using 1 minute interval. So for every 1 minute interval, I am doing the calculation for each cube. Okay. It takes 7 into. Yeah. To forecast the weather for 7 days using 1 minute interval, it takes 7 days into 24 hours per day into 60 minutes per hour into 10 power 13. That is, so 10 power 17 floating point operations per second we need. Okay. A computer operating at 10 gigaflop, 10 power 10. Gigaflop is 10 power 10. Okay. Floating point operations per second. It takes 10 power 7 seconds. 10 power 7 second is 115 days. To perform calculation 50 minutes requires a computer operating at 34 teraflops. 34 into 10 power 12 floating point operations. So my desktop has 4 cores. Base clock frequency is 3 GHz. That means my laptop has 0.384 teraflops per second. So definitely it is impossible for a laptop or computer to do 34 teraflop operations per second. Okay. Tera floating point operation per second. Okay. So we need HPC or supercomputer. So earlier it was supercomputer approach, now it is HPC approach. So we are getting the commodity servers from the market and we are interconnecting with the special InfiniBand switch, and we are dividing the problem, decomposing the problem into several chunks and getting solved by each server and getting the result back. Okay. Okay, similarly, other example similar to weather prediction. So say MD simulation, molecular dynamic simulation. So to simulate a biomolecule of non-bond energy term from for 1 microsecond simulation. Okay. So we need, okay, for atom size increases, we need the number of operation is more. Okay. So normal computer cannot do this. So we need HPC. Okay. Yes, HPC means high performance computing. Yeah. So you can see this is the top 500.org list. This list is updated every 6 months. Okay. So here the top supercomputer in the world now is Captain. Okay. So it has this many cores and its teraflop is, it's a petaflop, 10 power 15. Okay. So it's 1742 petaflop. So this much calculation can go. So R peak is the theoretical value. This is the practical value. Usually it is 60 to 70%. Okay. So this is through benchmark HPL, high performance LinPack benchmark. There is one software. So high performance LinPack. LinPack is linear algebra subroutine package. So basically we are running the linear algebraic equation, because in the initial slide only I told. So we are converting the physical model into a computational model, that is mathematical model. Then mathematical model, what we are getting is in the form of partial differential equation. Since partial differential equation cannot be solved by digital computer, we are converting it into algebraic equation, linear algebraic equation. That algebraic equation is getting solved. So this benchmark program, high performance LinPack is linear algebra subroutine. So it has a lot of problems. Okay, so it tests the computer capacity. Okay, so that programs are used for benchmarking. So after benchmark, usually it is 80% or 70% will get. Okay. So these are all the, so it is, so supercomputer or HPC. HPC is mentioned as how much teraflop it can perform. Okay. Similarly, India list also we have top CDAC, top sc.cdacb.in. This is the India list. So here it is 81344. So this is Rmax, Rpeak. Rpeak is the theoretical teraflop. Here it is teraflop, not petaflop. So here, so it's, you can just make it say 8 petaflop, 8.5 petaflop Rmax. Okay. So that's why, HPC will be measured in terms of how many floating point operations it can do. Okay. Okay. So what is basically HPC is? HPC is nothing but it's a collection of commodity servers. Okay, it's a collection of commodity servers interconnected with some special type of network and some special type of storage for its need. Okay, so why we are interconnecting the servers? So whatever servers available in the market, we are purchasing n number of servers, and we are using some special switch for interconnecting it. And the larger problem we are giving, and the problem is getting divided, and through parallel computing we are solving the big problem. Okay, so each and every part is given to different server, and we are collecting the result. Okay, so basically it has three components: compute, network, and storage. So compute, it can be CPU, it can be GPU. In future we can integrate QPU also, quantum processing unit also. And network, so usually what network we are using? We are using Ethernet network. So Ethernet is there for a long time. So why we need special network? InfiniBand. IB is InfiniBand. Okay, IB means InfiniBand. So why we need this special type of network? Because Ethernet can give bandwidth, no issue, but latency, the delay will be more. So here we are passing the information, okay, from one node to the other node, because all, for example, 10 nodes, all 10 nodes are solving a single problem only, different part of the single problem. Okay, since all the servers are solving different part of the single problem, okay, they need to communicate each other, okay, in order to do the computation. So that communication should not be a bottleneck, because if communication is delayed, the computation will be delayed. So communication should not be a bottleneck. That's why we are changing the Ethernet to InfiniBand switch. So how changing from one network to another network improves the performance? Because this technology is completely different from what we are using in Ethernet. In Ethernet we are using TCP IP protocol. In InfiniBand we are using remote direct memory access protocol. So I think everybody has know about the DMA concept, direct memory access protocol. So here InfiniBand switches uses remote direct memory access protocol, so that it bypasses the encapsulation decapsulation cycle. So it completely bypasses the ISO OSI layer stack. Okay, so all the intelligence are in the network interface card itself, NIC, that is called IB card. Okay, and then why we need special type of storage and special type of file system? It is called PFS. It's a parallel file system. So parallel file system is needed because again I am telling, so single big problem is divided into different chunks and it is getting executed by different servers. So it is single problem. So input file will be same and output file should be same. So it should read concurrently and it should write concurrently. Okay. So concurrent read and concurrent write is only possible with parallel file system. Okay. Oh, sorry. Yeah. Sorry. So what is the core components of HPC? So it is compute, network, storage, on top of it scheduler. Okay. Users, okay, there are multiple users. So there are multiple users, they will log into the head node and they will submit the job to the scheduler and the scheduler will allocate the node and storage. Okay. Okay. So interconnect. Okay, how we are interconnecting, why it is important. So Ethernet, initially it started with 3 Mbps bandwidth. So this is bandwidth, okay. Now it can give up to, it can deliver up to 400 Gbps. So no issue. In terms of bandwidth, absolutely we have no issue, okay. But when it comes to latency only, Ethernet is lagging behind. Ethernet is, okay, it's good for bandwidth, for high bandwidth and low latency. So we need high bandwidth and low latency. Okay. So InfiniBand started in 1999 by Mellanox company, Israeli company. Now it is taken over by NVIDIA. Okay. So where Ethernet is not possible. Okay. InfiniBand protocol stack is considered less burdensome than the TCP protocol required for Ethernet. So TCP UDP latency is 3 millisecond. Okay. InfiniBand latency is below 3 microsecond, below 1 microsecond. So here EDR is 610 nanosecond only. So this is the latest NDR. It is 450 nanoseconds only. So latency is much less than Ethernet. Okay, this is RDMA over converged Ethernet. That means remote direct memory access protocol only you are using, but the physical medium is Ethernet itself. RDMA over converged Ethernet. So physical medium is Ethernet only, but the protocol only changed. But here EDR, HDR, NDR, this is part of InfiniBand topology terminology. Extended data rate. Okay, this data rates 200 Gbps. This is 400 Gbps. This is maybe EDR is 100 Gbps. HDR is 200 Gbps. NDR is 400 Gbps. This is about bandwidth. These are the latency details. Okay, so here we are changing both the protocol and the medium. Okay, in RDMA converged Ethernet, we are changing only the protocol from TCP to RDMA, but the medium we are using same Ethernet, but that also gives some advantage. But always this entire medium change and protocol change will give more performance. So it's a RDMA, remote direct memory access, to reduce CPU overload. So CPU will not be involved in the IO. Okay, CPU will be offloaded completely. So CPU will do only the computation task. This RDMA, this okay, this HCA, host control adapter card, will do all the network things. So here you see TCP, it goes to every stack, application layer, socket, transport layer, network layer, all layers it goes. Okay, here encapsulation, here header removing, decapsulation is happening. But here you see directly application is directly contact to or NIC. Okay, RDMA enabled NIC, network interface card, and RDMA over convergence, or it can be EDR, XDR. Okay, medium can be anything. Okay. So then storage. So basically HPC has three components: compute, interconnect, storage. The storage, because we need, since we are computing, since we are using multiple servers to compute a single problem, single big problem. Okay. So each computer has to communicate with, each process has to communicate with each other. So inter-process communication is more. So we need concurrent read and concurrent write. So that's why we are using parallel file system. Some of the famous parallel file system is Lustre file system. GPFS file system, and PNFS, parallel network file system. Okay, so here distributed file system, concurrent read is possible, but concurrent write is not possible. But in parallel file system, okay, concurrent read and concurrent write is possible. Okay. So throughput, performance, scalability. So there are many in cluster. There will be 1,000 nodes. So it can be accessed by 1,000 clients also. No issue. Low power, low management cost for huge capacity. Okay, if the capacity goes, okay, the cost will reduce. But for smaller capacity, the cost is very high. So here actually metadata and the actual data will be separated. Okay. So metadata performance low compared to many separate file system, because here metadata is separated. Okay. Metadata is separated and it is stored in separate partition, and object storage is stored in different place. Okay. And kernel, native kernel support is not there, so we have to compile the kernel and we have to change the Linux OS little bit, so that only then only we can install PFS, because native kernel does not support PFS. Okay. Any doubt? Okay, so just I will log in our HPC and I will show you some demo. Okay, just you can see how HPC is there and how people are using. Are you able to see my screen?
Visible.
Okay, okay, sir. Yeah, so here this sinfo, these things are scheduler command. Okay, we are using slum scheduler. Okay, slum is a open source scheduler. Throughout world, all big HPC they are using this scheduler only. Simple Linux utility for resource management. So in HPC, what are the resources? Resources is CPU, memory, network, IO. Okay, so basically four resources, but mainly it is two: CPU and RAM. CPU, RAM, network, storage, all are resources only. So to manage the resource, we need a resource manager. Okay, so that is actually Slum, simple Linux utility for resource management. Okay, Slum, simple Linux. Simple Linux utility for resource management. Slum scheduler. So here actually, so these are all the nodes. Allocated means it is allocated and people are using it. I think I will reduce the magnifier then. Okay, so this many, because screen is big actually. So we have this many jobs now running in the HPC. So PD is pending state job. Okay, PD is pending state job. So there are so many pending jobs and R is running jobs. Okay, so now I'm just counting it. Grub PD WC-L. That means I'm just counting. There are 650 pending jobs. Okay, and there are 137 running jobs are there now. Okay, for example, now if I take this job, okay, so this job is running in 10 node. Okay, 65 to 65, 66, 67, 82, 83, 94. So this one node has 32 core. That means it is running in 320 core. Okay, each node has 512 GB RAM. Okay, so whether it uses actually 64 GB only, but each node has used is 64. So that means at least approximately, if you do so, it is using 640 GB RAM. Okay, I'm just multiplying it by 10. It is actually using 640 GB RAM and 10 into 32, 320 cores. Okay, so it is what he is running. He is running KKR flex exe, some executable he's running. Okay, so these are the master node. Here is a master node. Okay, so this is the scheduler commands. So how they submit the job, just I will show you. There is a job script. Yes, control show job. I'm just finding out what job script he used. So this is the script file he used for submitting job in cluster. Okay, I'm just showing it so that you can understand. So this is the script file. Okay, so this is the slum scheduler script file. So directly we cannot execute anything in the compute node. User cannot log into the compute node directly because it is through scheduler only they can access the compute node. So from the master node he should submit the job. Okay, he is requesting, okay, he's telling his job name is a angel 4 partition, that is queue. Okay, there are a lot of queues. Okay, queue state hyphen queue, there are a lot of queues in the cluster. Okay, if you submit in short queue it will run for 8 hours. If you this we can define it. Okay, if you submit in single queue it will run for 72 hours. Small queue, what is the minimum node, what is the maximum node, all these things we can define. Based on that they will select the queue. Okay, so based on that they will select the queue. So he's mentioning which queue. Partition means queue, which queue he want to run. And per node it is 32 core. So he want 10 such nodes. That means 10 into 32, 320 cores he need. Okay. And output file he is mentioning. And just echoing this line. Okay. So job started at date. So date, this is a command. So it will bring the that time date. Okay. So it will bring the date. Then he is just loading the modules and executing this executable hyphen np slum. Here the 320 will be substituted, so the same program will be running in 320 cores. Okay, so this is how user is submitting. So this is the script file. You will just submit s batch, that script, so it will go into the queue. Okay, if the resource is available it will start immediate running. If the resource is not available it will wait for the resource. Okay, till then it will be in the pending state. So this is about compute. Okay, then network. So this is the network we are using, that is EDR 100 Gbps network. Okay, we are using 100 Gbps network. Okay, this is the MT410 is the host control adapter card, that is the RDMA enabled NIC, network interface card. Okay, so this is the InfiniBand card we are using. And status, so it is link 4x EDR. So EDR rate is 225 Gbps. So but EDR has 4 lanes, so each lane capacity is 25 Gbps. So 4 into 25 it's 100 Gbps. Okay, okay. And then about storage, so we have Lustre file system. Okay, this is the file system storage. This is mounted. So this is the file system. Okay, okay. LSF get stripe. So here, okay, so here parallel file system, each big file will not be stored in one location. Okay, it will be divided into different chunks. That is called striping. Okay, striping. Then each part will be stored in different hard disk. Okay, then for reading you can read from different hard disks, so that if you are writing in the 4 disk, okay, your reading speed will be 4x speed. Okay, so better, so that and writing also will be in different files. So that's why you can do concurrent read and concurrent write operation is possible, because you are not writing single file in single location. Okay, shall we move on to the next section, or any doubt? Okay. Okay, whatever we have seen till now is HPC. Okay, HPC is compute. Network is InfiniBand network because we need high bandwidth and low latency network. And storage is a parallel file system because we need concurrent read and concurrent write. Okay. So now we will see about GPU architecture. Okay. General purpose GPU. Okay. GPU is graphical processing unit. When you use it for general purpose, it becomes GPU. Okay. So why we need it in HPC? CPU is designed to excel at executing a sequence of operation. So CPU is good, okay, but GPU has more ALUs. These all green parts are ALUs. So computer has ALU, arithmetic logical unit, control unit, cache memory, DRAM, everything. Okay. So this is a CPU. Okay. CPU is multi-core architecture. Okay, but GPU is many core architecture. Here the number of cores will be 1000, 2000, 1 lakh also. But here it is maximum 64 core, 128 core, 191. AMD Epic has now come up with 192. Maybe they will go up to 256. That is a maximum in multi-core architecture, 256. But here in GPU, even low-end GPU card will have thousands of ALUs. Okay. So for highly parallel things, it is very good. GPU is very good for highly parallel things. GPU give massive parallelism, high throughput, energy efficient because number of floating point operations is increasing because floating point operations depends on the number of ALUs because in CPU we have fused multiplication addition. Okay, FMA for each core we have two FMA. One FMA can do two operation in one cycle. That is one addition and one multiplication. So that everything depends on the number of cores. Okay, so here number of cores is more. So automatically the number of floating point operations per second is more. Okay. So we get more teraflops from GPU and power consumption. It is 4 times less for teraflop. Okay. For example, for 10 teraflop, if you are using 10 kilowatt, okay, same 10 teraflop from GPU, you will use only 4 kilowatt. Okay. So it's a 4 times less, but all application will not give, but if it is highly parallel then you will get more advantage. Otherwise for sequential things, CPU is powerful. Actually CPU is more powerful than GPU since it is more in number. The number of cores are more in number in GPU. Okay, so they are getting more parallelism. Okay, but powerful cores are CPU only. CPU is general. CPU yeah, common general purpose CPUs are very powerful than general purpose GPUs, but parallelism is more in GPU. So memory also is a graphic DDR6, high bandwidth memory 2, 3. These technologies are there. Okay. So normal graphics card won't have its own RAM, own memory, but this add-on cards will have its own RAM. Okay, GPUs for mainly it is depends on how much GB RAM it has. Okay, okay. So host is CPU only, device is GPU. Okay, so host is always needed to control the device. Device cannot operate on its own. Okay, so always we need CPU to perform operations on GPU also, because initialization will happen through CPU only. Okay, back and forth it will compute, and now unified memory architecture has come. Okay, so device refers to GPU and host refers to CPU. Okay, so the connectivity can be PCI, peripheral component interface extension, or some NVLink. NVIDIA's proprietary things are there, NVLink and other things. Okay, and InfiniFabric is there. So AMD also has GPUs. So okay, so here just this is the anatomy of NVIDIA A30 GPU. Okay, this is the Amber architecture. It has 56 streaming multiprocessors, total 7,168 CUDA cores. See, here you see 7168, but in CPU maximum very latest is 256. So tensor core. So it has three types of cores: CUDA core, tensor core, and RT core. RT is a ray tracing core. Okay, that is also there. So mostly GPU has three types of core: CUDA core, tensor core. Tensor core will be designed for tensor operation. Okay, and then ray tracing core is used for graphics purpose. So total 56 symmetric processor, 128 CUDA core per SM. So 128 into 56 is 7168. So teraflop is the peak tensor performance. So peak is 10.3 teraflop, 330 for tensor performance with sparsity matrix. Okay. So this is the GPU. Okay, memories are connected here, and each GPU has, for example, this GPU has 8 GPC. Okay, graphics processing cluster. GPC is graphical processing cluster. So each GPU has 8. This is not common for this model. Okay, so GPU has 8 GPC graphic processing cluster, and each GPC has 8 TPC, and each TPC has 2 symmetric multiprocessing, 2 SM. Okay, this is a TPC. Each GPC is shown separately, and here TPC. So GPC is graphics processing cluster, texture processing cluster, and 2 SM per TPC, and 4 process blocks per SM. Okay. So these are single position. Okay. So 4 process block per SM, 16 floating point 32 core per block, or 64, 16 into 4, 64 cores per SM, because each SM has 4 blocks. So 4 into 16 is 64. Okay, 16 integer 32 core per block, then again 64 per SM, because 4 blocks per SM. Okay, so like that it is there. Okay, so this is how internally it is there. Okay, so we need to program that explicitly to get the advantage. Okay, so special function units also there. So integer, floating point. Apart from that, special function unit is there. Trigonometric function, exponential function. So this can be done directly with this hardware. Okay. 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 Now we will see CUDA Q. So in order to run CUDA Q, okay, compute unified device architecture. Okay, so it's a quantum for CUDA for quantum. So to run CUDA, you need at least compute capability of the CUDA, that is GPU card, should be at least 7.5 and above, 7.0 and above. Okay, then only CUDA can be supported. The older GPU cards will not support. Okay, for example, this is compute capability is nothing technical. This is a number actually given by NVIDIA itself based on its capability and new things. Okay, so this cards Kepler, it's a 5x. So you cannot run CUDA in this Kepler Maxwell Pascal architecture. From Volta only you can start running, that is V100, A100, these cards, RTX 2080. So these cards, okay. So while if you want to purchase or if you want to use CUDA Q, you should try some of the latest cards with compute capability more than 7. But now new versions are also coming. So better to check it and then we have to purchase it, because simply we cannot purchase and it will not support. So here thread and superset of thread is blocks and superset of blocks is grids. So this is how we have to program CUDA. Okay, small units of execution, that is called thread. Okay, then block, a group of threads that can communicate and synchronize running on the streaming multiprocessor SM. Okay, grid, a collection of blocks, the entire kernel execution. So kernel is the part of the code which is executed in that device. Okay, host is CPU, device is GPU. Okay, in future device can be QPU also. So whatever the part of the program which is running on the device, that is called kernel. Okay, what are the challenges in HPC? So floating point operations per second increase faster than memory access speed. So we are getting now 256 cores per die also, but not in single die. That is actually multi-glue technology. So in one socket we are getting 256 cores. But memory access speed is still, we are using DDR4, DDR5 only. So access speed is not increasing as much as cores are increasing. So we are having powerful cores, but next step is memory. Okay, next step is IO. So if there is a bottleneck in memory or IO, entire process will get slow down. Okay, so we need, so now at least CPU is very powerful. Now we should increase the memory bandwidth, and then IO also we should increase. Otherwise, if computation will be good, memory also good, but if IO, if reading writing is happening at very slow speed, so the idle cycle of the processor will increase. If so, that means the processor will not do any job for some certain amount of time. Okay, increased clock speed and density leads to higher power consumption. For higher power consumption, we are going for new type of cooling. Okay, so DCLC. Okay, direct to chip liquid cooling, DCLC, direct to chip liquid cooling. So now a lot of cooling techniques are coming because the GPUs are producing more heat. So more heat means, so more power dissipation. Okay, so now people are working on reversible computer also to reduce this heat, so that reversible logic will not produce more heat. So that is also another field which is coming up. So processor wait for data, limited performance. So processor is wait for data means, so then read write speed is very less. Okay, so processor is completing the job, but it is waiting for writing the data. So processor is ready to process the data, but it is waiting for the reading. So if IO is slow, that entire process will be slow. Cooling and energy cost limit scaling. Okay, so cooling and energy cost is very high now. Increasing flop without memory bandwidth is inefficiency, because CPU need data from the RAM only. Okay, A plus B means A and B should come from RAM. If it is delayed, okay, then CPU idle cycle will be more. Okay, so bandwidth also should be, so that you can take 64 byte, 128 byte at once. In one cycle you can take 128 bytes. So bandwidth also important. Need for energy efficient high performance computing, so they are thinking for alternate. Okay, like ARM, advanced risk machine based processors, or FPGA based, because now we are using x86 architecture. X86 only Intel and AMD is applying, but when it comes for ARM, advanced risk based machines, so many players are there. So and it consumes very less cost, but the complexity in the program increases. Okay, yeah. Okay, so now we will just brush up the concept of quantum computing. So quantum computing, mainly it is superposition, entanglement, interference, and coherence. Okay, these are all the four main concepts. So what is quantum? Quantum means nothing but it is mentioning the size of the particle. Okay, if whatever things, okay, if it is 10 power minus 9 to 10 power minus 15, that is called quantum particle. Okay, so what are the quantum particles? Atoms, ions, photon, subatomic particles like positron, quarks, everything is, okay, quantum. Anything at the scale of atomic and subatomic particle is called quantum. 10 power minus 9 to 10 power minus 15 is called quantum. Okay, if you are using this quantum particle to do a computer, okay, then it is called quantum computer. So basically we are dealing with atoms and subatomic particles. Okay, for doing computation. Earlier we are doing computation, now we are doing computation with the help of transistors. Okay, so transistors is the basic components. So with the transistors we are building the gates. With gates we are building the circuits. With circuits we are using circuits, and algorithms, then we are computing. Okay, we are doing calculation. Similarly here, there it is transistor, here it is subatomic particles and atoms or electrons, electron, protons, photons, these things are all used. Okay, instead of transistor we are using this. So we are manipulating these things. Okay, we are manipulating the atoms or electrons position, okay, momentum. Okay, we are manipulating this and we are doing calculation. So if you are doing because since it is quantum particle, we are manipulating quantum particle and doing calculations, it is called quantum computation. So next generation paradigm beyond classical computing, because even HPC, because even the largest HPC cannot solve many of our real world problems. Okay, that's why we need either exascale level, because teraflop, petaflop, exaflop level HPC require more electricity, more cooling, and even exascale will not be sufficient for certain applications. Okay, that's why now we are changing the complete thing. Okay, for high performance computing, so quantum computing will be an actually accelerator. So here we use qubits instead of classical bits. Qubits can be in 0, 1 or both superposition. That is actually he uses a parallelism. Quantum algorithm leverage parallelism inherent in quantum mechanics. So quantum mechanics is 100 years of science. Okay, now we are using it for computer. Okay, for computing. So there are a lot of concepts. So here, so in the normal computer we write code, we write program, and that program is converted into machine code using compilers. Okay, that machine code is then pre-processed. Okay, preprocessor then processed. Okay, then processor has what logic gates only. So it is getting solved like this. But in quantum it is first you have to prepare the qubit. The qubit can be prepared by any method, but here in normal classical computer, always logic gates are with the transistors only, either npn or pnp. So it's a NAND gate or gate, all are transistor only. The basic element is transistor only. Here in qubits, the basic element can be electron, can be proton, can be photon. Okay, so it can be any of the subatomic particles. Okay, or Majorana like that. So now Microsoft told that they developed something. So any particle, okay, that is between 10 power minus 9 to 10 power minus 15. So any particle, with that any particle you can create qubits. After that qubit, okay, so we are giving some energy to the qubits to manipulate it. That is called quantum gate. It's a matrix. Okay, it's a matrix, or it's an external force. You can say quantum gates is nothing but it's an operator. Quantum gates is an operator. Its operator is nothing but a force. So qubit is a, for example, if you consider qubit is an electron, so you are applying some force on the electron to move this electron from one place to another place. So that is a gate operation. So if you apply this gate operation, okay, this electron will move from one place to another place. That is, it is changing its state from one state to another state. So if you apply quantum gates to the qubit, it will change its states. So qubits can be in n number of states, but we are concentrating on only two states, that is 0 and 1. That is called qubits. Okay, so electron can be in n number of states, but we our interest is only in two states. Okay, quantum gates. Then with multiple quantum gates, you are creating quantum circuit. Then this quantum circuit is getting solved using quantum processor. Any doubt? Yeah. Okay. Yeah, I will share something. Yeah. I'll share this PPT also. So HPC actually, yeah, there are a lot of introductory videos are there. So control, manage, schedule all task management, backend accelerators, GPU. Yeah, right. So GPU, TPU, NPU, neural processing unit, tensor processing unit, IPU. So generally you can call it XPU. X can be substituted with almost now many alphabets. So it's XPU. Okay.
Sir,
DPU.
actually, many of them are from non-computer science background also.
Okay, okay,
Hence, many of them may be new to HPC, so you can
okay, okay,
consider.
okay, okay,
Thank you,
okay.
sir.
Yeah, thank you. Yeah, absolutely. We can see the difference. For example, if 10 node job, if it runs one node, it takes more time actually. And there is a concept called scalability. Okay. For example, 10 node job, if you run in 100 job, will you get 10 times faster? No. The application should be capable of scaling. Okay. Otherwise, what will happen? Communication will be more and actual computation will be less. That is actually, for example, if you say one person is doing job in one day, if you deploy 2%, the job will get finished in 12 hours. Okay, 4%, 6 hours. But beyond 4, okay, if you add, all the employees will talk to each other and no work will happen actually. That is called scalability. Okay, so okay, up to 4 is scalable. After 4, the performance will degrade. That is a scalability. So simply there is a Amdahl's law and other laws are there. How the scalability is there. Okay, that things, yeah. So simply increasing number of cores will not scale. So your application should be scalable to that level. After certain limit, it will not scale actually, because you have to rewrite the application based on that. Okay, so prime factorization of bit integer computation that are handled by HPC over quantum computer like prime factorization. So prime factorization is not possible by HPC now, because that is depends on the number of digits you are using. If it is small number, it can be possible, but if it is a 256 bit or something, then it is not possible by HPC now. Even now in quantum computer also theoretically it is possible, but still now, to my understanding, I think nobody has broken it. Real prime factorization which is used in RSA algorithm, I think nobody has broken it. It takes too long. Possible to make a handheld quantum computer? I don't know, but there are some tabletop NMR based quantum computers are available. Handheld, I don't know, but tabletop is available. Tabletop quantum computers are available. It is NMR based, nuclear magnetic resonance based. That is available. No, QPU is okay. So entire computer cannot be replaced by quantum computer. Okay, so quantum computer where actually we need parallelism, high parallelism, okay, for some scientific application, which now at present we cannot solve using the classical HPC. There only we will apply, but otherwise for other tasks, existing computers well and good. For gaming is, but high parallelism is there. Okay, wherever parallelism is needed, you can do that. But for gaming, I don't know. Hardware accelerators. QPU itself accelerated for HPC. Okay. Common man, usually it is security. Okay. So everybody is involved in security. If our passwords are cracked using quantum computer, definitely we are going to suffer. So security is the complex problem. Optimization. Apart from that, security is the main thing. So mainly it is security and communication. Communication is also now military communication, secret things. So key sharing. So now at present, most of the focus is on communication and cryptography. Yeah. Computing, yeah, like chemical reactions, everything we can do. For example, now variable quantum eigensolvers, finding the lower energy. So those problems actually it's very hard for HPC also now. But we have to integrate actually. Some part has to be done. That's why hybrid comes in. Some part we can digital, yeah, digital twinning. I think it's not. It's not for quantum computing. Yeah. Okay. What is hardness? Quantify the hardness or hardness level. Okay, I did not understand this. Hardness level means in computing. Yeah, so right now this non-polynomial things. Okay, so those which are in NP hard, those which are not able to solve. Okay, but if quantum computer comes, we may solve it. Okay, exponential problem. Okay, so basically two things. So problems which can be categorized into two things. One is polynomial time and another is exponential time. Okay, so polynomial time, drug discovery, everything we can do. So polynomial time computation can be done using classical computer. But if it is exponential, okay, because for example, if I am doing some lower energy calculation or something for some molecule which has two atoms, hydrogen, let's say. Okay, that is possible. But if I take a bigger molecule, that is not possible with HPC because too many combinations are there. Okay, if I do it also with HPC, if I increase one more number, okay, then for example, 2 power 2, if I just one more number, then I need similar size of HPC, double the size of HPC to compute that problem. But here in quantum, if I add one more qubit, that will do. Okay, drug discovery is there because we have to check a lot of possibilities, 2 power n combinations. So here in quantum computing we can do all at once. Okay, in other things many combinations are there, we are doing one by one checking all the things, but here parallelly you can do all combination and we will get the right result. Yeah, definitely optimization problem. Now D wave, this quantum annulars actually they are mostly dealing with optimization problem. This Volkswagen route optimization they are doing a lot of. Qubit can applicable to all computing. Qubit is applicable only to quantum computer. So bit is for classical computer, quantum bit is for quantum computer, and the only thing is it can be in 0, 1 or both. So it can be in multiple state at once. Okay. Actually we cannot identify where it is. For example, if the electron is there, okay, you cannot find out where it is. So you can say, for example, what is superposition is, okay, so you are inside your home, I am outside your home. Okay, I know you are inside because I have seen your okay footwear or somewhere, okay, in the outside, and I conclude that you are inside. But I cannot say that you are in the hall or you are in the kitchen or you are in the bedroom. So till I measure, I don't know where you are. So I am telling it is in superposition, but it is in, it is you are in the home only, but I don't know exactly which position. That is called superposition. So atom are in, so we can say probabilitically. It's okay. Probabilitically, he can be 50% in the hall, 50%. If I enter your home and if I see you, okay, physically, okay, you are in hall, then that is called measurement. So after measurement, the quantum state collapses. I have no doubt. I have seen you, so you are in the hall. So that is the measurement. Okay. This procurement things I don't know, but QPI actually they are also India they are making it. except cryogenic cooling, everything is make in India only. Yeah, and some tabletop NMRs also there in China, I think. So mainly Qiskit, CUDA-Q, okay, and Google's and bracket. There are a lot of. There's the measurement log analysis. No, after measurement, you are getting a value. Okay. Yeah, after measurement, yeah, it's a superposition collapsed. It become classical. That's why measurement we need in Qiskit circuits and all. Measurement circuit we are putting in the classical register. After measurement, it become classical. Yeah, it will come to either 0, 1 or some probability. Okay. There is no such thumb rule till now because we do not have QPU till now. QPU, we have QPU separately and HPC separately. There are a lot of work happening to integrate this. Okay, till now it is in the experimental stage only. So that in that case, okay, where the high parallelism is there, that part you can give to QPU and get it done, and remaining will go in HPC itself. So hybrid programming also needed. Okay, it's not only hybrid architecture but hybrid programming. That's why this CUDA Q is will be because CUDA already GPU is a accelerator. They successfully integrated with the HPC. Okay, maybe in future any QPU can be integrated with the HPC, and this CUDA Q is the same platform. Okay, it's not only simulator, it's a emulator also. So you can run the code and that kernel will run in the QPU. So but now still that integrate, but CUDA Q platform will work even if a hybrid HPC quantum comes in. Yeah, qubit will be used in LLM models. Yeah, if for machine learning it is needed. Okay, so what is parallel computing and high performance computing? Both are same only. High performance computing is parallel computing and high performance HPC is same. Parallel computing is just low level technical term. High performance computing is just a broad level technical term. That's all. Both are same. HPC without parallel computing is nothing. Quantum computing is not parallel computing. Actually, it by nature it has more parallelism because for example qubit, it can be both in 0 and 1 or both at a time. Okay, and entanglement also with multiple qubits there is a, so you can do many similar tasks, many simultaneously. You have to do, you can do lot of tasks. That is inherently parallelism is there in quantum computing. So parallelism is what? Okay, I am doing one work now, simultaneously I am doing another work. That is parallelism. Okay, so in qubit, if it is in 0, okay, you do this one. If it is 1, you do this one. But if it is both 0 and 1, it will do both the job at the same time. So that is parallelism. Okay, so quantum has inherent parallelism. HPC we have to specify it. Okay, if I have 64 core, okay, first core you do this job, second core you do this job, third core you do this job. So then you have collective the communication. NPU is neural processing unit. Now even this Apple chip M1, M2, M3, M4, M4 I think new latest is M4 chip. So M4 chip also comes with CPU, GPU, NPU. Okay, or QC applied, sir. So no, NPU is actually like tensor processing unit. There is no QC actually. Now desktops M4 processors of Mac comes with NPU. No, three qubit computer you cannot do much. See, computation needs minimum thousands of qubit, and that too logical qubit. If you have 1,000 physical qubit also, it is not sufficient, because we don't know the what is the mapping. For example, one logical qubit may be 7 physical qubit or 20 physical qubit. So it depends on the quality of the qubit. So with 3 qubit, maximum you can do is communication things you can try. Key distribution things, those things you can. Yeah, M5 has come, I think. Okay. Yeah, quantum physics is yeah, physics only, mechanics, but quantum is in nature actually. Quantum is in nature. So like so nanotechnology came. So nanotechnology actually, if in the nanoparticle level, the properties changes. For example, sugar gives sweetness, but in the nano level sugar it may bitter also. So when the size reduces, okay, the behavior changes. So for example, the Newton physics applies to all these mechanics. Okay, classical mechanics, everything based on the Newton physics. Okay, if I give this force and this angle, okay, this particle will go from this place to this place. Okay, without throwing that object, I can predict the where it will go if I send this particle in this speed. That is classical mechanics. But the classical mechanics fails when the size of the particle is becoming less. That is quantum. Okay, in the quantum nature, the classical physics fails. That's why Schrodinger, okay, Schrodinger created an equation called Schrodinger wave equation. Okay, and there are two types of wave equation: time dependent and time independent wave equations. So he told, okay, classical mechanics, that Newton mechanics will not work for quantum. So he developed a different equation. Okay, so in that equation, if you apply the things, okay, then you will get the position, but you cannot, there is a uncertainty is there. Okay, uncertainty is there, Heisenberg uncertainty is there. And if you find the position, you cannot find the momentum. If you find the momentum, you cannot find the position. So that is actually, yeah. Yeah. So this is Moore's law is getting broken. Okay. So he's an Intel scientist. He told that every 18 months and the processors in the chip will get doubled. Okay. That means now one person is buying a laptop, another person is buying after 18 months. So he will get double the performance with the same cost. That is the prediction of Moore's law. So when there are yeah, scaling, lot of problem comes in. Okay, so the transistor size getting reduced, 2 nanometer now, 2 nanometer. So it does not that emitter based collector actually leaking. Okay, so tunneling happening between, because if current passes through emitter base collector, so tunneling happening, so it does not follow the rules. Okay, when the size is reduced, it does not follow the rules. It has different rule. For quantum world, it has different rule. So we cannot make the transistor. Okay, then error will be more actually. It will not work as intended. Okay. Yes, because of that only we are going for quantum computer. Otherwise, we will be reducing the size and we will be increasing the number of transistor and we will be increasing the computation. But that is not the only reason. Size reduction is also a reason, but that is not the only reason. Now too much power is being used. For same calculation, if you have a proper quantum computer in future, with very less power, we can achieve that computation. So that is also power. Electricity issue is also problem. Cooling issue also problem. Size is also a problem. Yeah, machine learning. Yeah, machine learning. So what everybody is telling, for artificial intelligent, whatever the existing HPC or GPU forms are not the right hardware. The right hardware is yet to come. That is quantum. Then only we know the real power of AI. Definitely, you can, since quantum has more parallelism, so you can number of parameters you can increase, so that accuracy will increase. So QML also will get benefited. Yeah. Shall we go with the session? Just yeah. Yeah, for artificial intelligence, the right hardware is not yet come. The right hardware is quantum only. Software is AI, hardware is quantum, not HPC. Yeah, field is not a problem. Any field is good. Which network topology? They are trying many topology. Each, for example, IBM has lot of quantum computers available in the cloud. Each quantum computer follow different topology. That means qubits arrangement is called topology. Okay, so it can be arranged in any order. That's why you are writing a qiskit program or whatever program, that is getting transpiled to that hardware specific. Okay, that is called transpiling. So compiling is high level to machine level, but transpiling is machine high level to high level only. Okay, so the transpiler will take care of the underlying hardware and topology. That is also very challenging. Topology is very challenging. Biocomputer, I don't know, but a reversible computer, but it's all coming on. Reversible computer, reversible logic gates, so that less power reduction, power usage will be very less, and heat will be less. Yeah, I know I don't know much about QML, but yeah, quantum machine learning is coming. Yeah, good topic on. Yeah, okay, we will see. Okay, so superposition, so it can be in both the state. Okay, 0 and 1. So 3 bits mean 2 power 3 states. So it can be in 0, 0, 0, 0, 0, 1, 0, 1, 0. So it can be in any state. So it's a qubit is nothing but electron or proton or neutron. Okay, so it's just subatomic particle. So it can be in any position. Any position means it can be in any location. That is a state. So entanglement, strong correlation between qubits beyond classical probability, because for highly parallelism you need correlations. Okay, so one particle should be correlated to another particle, then only you have that correlation. Okay, then only you can have parallelism. Quantum teleportation, quantum key distribution, speed up in search and optimization, everything is possible through entanglement. So entanglement and superposition actually creates the parallelism. Okay, what is a QPU? Quantum processing unit. So the quantum particle can be in any state. Okay, it can be in n number of state, but we are focusing only on two state, 0, 1. Okay, two level quantum system called qubits. Unlike a classical bit 0 1, so this is, it will be in superposition both states. Multiple qubits can interact via entanglement and interference, enabling exponential parallelism. Okay, so entanglement and interference produces the parallelism. With n qubit, a QPU can represent 2 power n states simultaneously. If it is 3, 8 state, 4, 16 state, 5, 32 states. Okay, 6, 64 states, like that. So superposition plus entanglement is equal to quantum parallelism. So superposition 0, 1, and then entanglement, it gives quantum parallelism. So we have a lot of options to produce qubits. Trapped ion, you can trap the ions and manipulate it, or you can use superconducting qubits. Okay, superconducting qubits. So trapped ions, just you are using laser lights for manipulating it. Okay, if you just pass a light on that, its position will change. That means its state is changing. Okay, and microwave pulses for superconducting qubits, so its position is changing, so its states is changing. So qubit fundamental units, superposition can exist in multiple states, entanglement, strong correlation, quantum gates, unitary operator that manipulate qubit state. That is the force which you give on the qubit to change its position or momentum. That is a quantum gate. Okay, or spinning, whatever it is, quantum gate. Okay. So measurement, collapse superposition state into, that is, I told you one example. So if I enter the house and if I find the person, he's a particle, okay, and I know exact position, okay, then the quantumness is gone, okay. Noise and T coherence, physical limitation affects QP reliability, because here temperature, because we have to maintain the right temperature, otherwise the environment factors will affect the position, okay, momentum, everything it will affect, so that you cannot calculate, the state will keep on change and you cannot do any computation. Scalability challenge, increase qubit count and fidelity for practical application. So here now, if you can increase the number of qubits also, it is very difficult now, because the coherence time is reducing. So it should be in the state until you do the calculation, it should remain in that state, so that you can manipulate it and you can do some calculation. But without your manipulation, if it is changing by itself because of noise, decoherence, then the error rate will be more. Many computation in one go, quantum algorithms, so a lot of quantum algorithms are there, cryptography, material, drug discovery, machine learning. So for these things we need quantum computing, not for normal applications. Okay, okay, so why quantum computer? Okay, HPC alone cannot solve this problem, we need quantum computer. Whether quantum computer alone can solve all this problem, that is also not possible. At least in near, at least for next 10 years it is not possible. Quantum computer alone cannot solve any of the problem. HPC need more power to solve those problems. Okay, quantum computer alone also cannot solve this problem. That's why we need a hybrid QC HPC for next generation computing. So quantum will act as a special purpose accelerator similar to GPU in early adoption. HPC remain primarily mature beyond. So okay, so now whatever quantum computer we have, it is noisy intermediate level, intermediate state quantum computer only. So it is not fully tolerant quantum computer. So it cannot operate at it on one. If it operates on one also, the result will not be correct. So result will be corrupted. So a few qubit, just hundreds of operations only we can do, because if you increase the number of qubits, circuits will travel by reaching that last qubit or something, that okay, because of noise or everything it will affect. So few qubits give result, but with few qubits you cannot do any real world application. Okay, high error rate, short coherence time, beyond that computation are corrupt. So short coherence time, the coherence time is lapse, so its states will change, so the computation will be corrupted. Okay, so HPC remain primary, mature, optimized for broad range of workloads. So already tested code, everything is there in HPC, tested interconnect, everything is there. So little part of the things we can offload to QPU and we can get the speed up. HPC proposed data and map problem to quantum format. Quantum execution selector kernel run on the QPU. So like now the CPU, QPU, GPU relationship in modern supercomputer in future. So if a GPU is an accelerator for floating point math, QPU is an accelerator for quantum probability amplitude. Okay, so GPU increasing the floating point operations per second. Okay, that's why we are using GPU inside HPC. Similarly, we will use QPU inside HPC because it will it is accelerator for quantum probability amplitude. Okay, so accurately we cannot say, probabilistically we can say, okay, this is the result. It will increase, QPU increases the probability amplitude. Okay, this is how the, so HPC, partial differential equation, discretization is happening, it is converted to linear system and iterated direct solvers. Then this is how it is executed in HPC. Quantum computing also will follow the same pattern, almost same pattern. So discretization, linear system, encode AB into quantum state. So here it is direct solver, here we are changing into quantum state, then amplitude. Okay, quantum state, for example, that psi is equal to alpha of ket0 plus alpha of ket1. I think everybody has told you. So that is alpha and beta are the probability amplitude. So what is the motivation? Quantum computer, limited qubits, number of qubits are very less till now. For actual to solve at least this crack this RSA algorithm, that is factorization, we need more qubits. The limited qubits we have, and those limited qubits also noisy. Okay, So n qubit state vector record 2 power n amplitude 50 qubit is, for 50 qubit at least you need 16 petabyte of RAM. That is not possible. So right now need scalable simulation on HPC plus GPU cluster. Okay. Okay. So why HPC is needed? Okay. Without HPC, even quantum error correction is not possible. So quantum error correction, QC encodes logical qubit using many physical qubits. Okay, requires real-time feedback from classical process. So quantum error correction also happens in classical only. Circuit compilation and optimization can happen in HPC. Control and scheduling will happen in HPC. Multi-QPU, that is quantum processing unit. Multiple quantum processing interaction will happen through HPC only. Without low latency HPC coupling, so we need, okay, QPU to QPU interconnection should be very, very low latency. Like in HPC, we use InfiniBand network. I told you EDR, HDR, NDR, InfiniBand networks. So like this, the low latency is very, very important for coupling HPC and quantum also. Or for coupling multiple QPU also, that network should be very, very low latency. Otherwise, we will not get the speed up. So state vector simulation, memory bandwidth bound, distributed parallel system, large data exchange. So network bandwidth is very, very important, and memory bandwidth is also very, very important. Okay. So quantum computers as accelerators. So earlier we are using GPU as accelerator. Now in future we will be using QPU as an accelerator for HPC, but it will not replace HPC. Tight integration is required since quantum computer cannot handle full-scale workload alone due to limited qubit counts, error rate, and memory constraint. Hybrid software stack need to be developed. So like I told you, Slum scheduler, simple Linux utility for resource management. So here we write, okay, this part of code run in GPU, this part of code run in CPU. So like that in scheduler also we have to tell, okay, which part to run in which processing unit. So middleware's libraries has to be, okay, code design, okay, hardware coupling, workflows, everything should be done. So this is Japan's Recurrent Computer Center for Computation Science. Quantum and HPC collaboration platform will be operating in 2026. So they are actually integrating it. This hybrid infrastructure mitigates error in quantum computing through linkage with HPC. See, this is the main point. This hybrid infrastructure mitigate error in quantum computer through linkage with HPC. So quantum error correction can happen with the help of HPC only. That's what I told here also. So quantum error correction is not possible without HPC integration. Otherwise, too many qubits will be needed. Okay. The goal is to develop system software for quantum HPC collaboration. Okay. Okay. So I think we will go for the demo. So quantum systems are hard to simulate classically. If you want to simulate also, if you want to simulate quantum system also, we need quantum computer, or at least GPU quantum simulators we need. Offload quantum kernels, allowing testing algorithm without physical QPU. So interconnect is very, very important. Interconnect plays very big role in HPC also, in quantum processing also. Because without interconnect, actually, if you use normal interconnect, whatever the speed of computation, so the entire thing is lost in the network itself. So high throughput, low latency link, InfiniBand, Omnipath, Ethernet, optimized for MPI. So like so QP quantum processing cluster interconnect is cryogenic, photonic, or microwave links between qubits. QPU requires phase coherence, entanglement, error suppression, so fidelity and coherent preservation. So we need both. Classical HPC interconnect, data exchange and control signal. For data exchange and control signal, okay, we need classical HPC interconnect, quantum interconnect for teleportation, entanglement swapping, quantum repeaters. Okay, so both needed actually. So balance speed of HPC interconnect is fragility of quantum links. So quantum links are very fragile. Okay, so this is actually, so speed and fragility gap. So HPC interconnect is having 8 lanes of good toll road, or so, and the cars are running in 100 kilometers per hour. But here quantum communication is happening like a bubble. Okay, small disturbance also bubble will burst. So we should be very careful here. So latency is sub millisecond, 100 to 500 nanoseconds for cutting edge techniques, InfiniBand, HDR, NDR, slingshot, RDMA over converged internet, NV link from NVIDIA. Bandwidth 200 Gbps HDR, 400 Gbps NDR, TBBS roadmap. Okay, so they have from GB to TBBS roadmap. They have robust protocol TCP or RDMA. So it is very good. So latency speed of light but limited by transduction overhead. Order of magnitude lower than megahertz to gigahertz regime bandwidth. Extremely fragile, decoherence, photon loss, error correction overhead. So here anytime the communication can collapse. Fragile. Okay. And interconnect for HPC is very speed. Okay, high speed interconnect, high speed and low latency interconnect. But here it's fragile. So too much research is going on this. Okay. Okay, how we will store KV, key value store database for QPU storage. QPU do not generate massive raw IO. What is that? So what is that maximum after measurement you are getting state vector. That state vector is nothing but 000 001. So very simple data only output. So you no need big storage. For HPC we need a parallel file system. For quantum processing you need database with key value store is enough. JSON format is enough. Okay. Usually few MBs since results are probabilistic. Okay, bit string. Only probability bit string we are going to store. Low latency KV database. So these are the database MongoDB, PostgreSQL can be used. Okay. So Kafka, RabbitMQ, many things are coming. So people are testing everything. So nothing is finalized till now. It's in lab only till now. So this is just key value format. Kit 0, this is state is equal to superposition, amplitude is equal to this one. So phase. So key value pair. Okay, JSON format, key value pair. So this is how it is stored. Okay, just I will, okay. So okay, if your computation problem inadequate classical solution, okay, then hard to compute, then can run on quantum computer, then data needed. So otherwise you go for classical only. Most of the things does not require quantum computer. If only this all are yes, then only you need quantum solution. Otherwise you can go for continue with classical solution, improve classical solution, monitor quantum computing improvement, explore quantum. So here if it is an inadequate classical solution, if there is no classical solution, then you go for quantum. If it is hard to compute, you go for quantum. Can run on quantum computer, can go for quantum. Data need suitable for quantum computer because you need inputs also to be in that format. Then you go for quantum. Okay, Kiski time skipping because today topic is okay. Okay, what is NVIDIA CUDA-Q open source platform for hybrid quantum classical programming? So programming environment is ready now for hybrid. Okay, so now we can master on CUDA-Q. When it is available, we can just explore that things. Hardware agnostics, seamless integration with classical space. So Python, C++, both it supports. Okay. Okay. Fundamental building blocks of CUDA-Q. So this is a CUDA-Q.kernel. Better I will go to the system. We'll just run and show you. So in this computer, we have one GPU card that is called NVIDIA A30. Okay, so in the slide, I have given this anatomy only. Okay. So I have installed CUDA-Q in this. CUDA-Q installation, I have the slide, no issue. So I'm just installing CUDA-Q with Anaconda package is highly recommended. You can just install the Anaconda package and then you can. Okay. So just C naught. So this is a CUDA-Q program. So import CUDA-Q. This is a Python based only. Import CUDA-Q. We are importing CUDA-Q and we are defining CUDA-Q.kernel. Okay. So from here only the kernel starts. Kernel means this part of the program will run in the GPU. Okay. So here we are Q vector equal to CUDA-Q vector of 2. That means vector. Okay. Each qubit is one vector only. Qubit is vector representation. Qubit is represented as vector in Bloch sphere. Okay. So we are just initializing 2 qubits. Okay, and for qubit, that is q vector of 0 and q vector of 1. So we are applying x gate, Pauli x gate for qubit 0, and then we are creating c naught gate, control not. Okay, c naught gate for 0 to 1, and then we are measuring the qubit 0 and qubit 1. We are measuring on z axis, mz. You can measure on mx, my, or mz. Okay, so result, we are writing it CUDA-Q.sample. So you can sample it, run it, or observe it. Okay, there are three different functions. So we are sampling it. By default sample, it will do 1000 times. So for example, in quantum and classical, what is the difference means? If I ask anybody 2 plus 2, what is the value of 2 plus 2? Everybody will tell 4. But in quantum computer, sometimes it will tell 3, sometimes it will tell 5, sometimes it will tell 6, sometimes it will tell 4 also. So you have to repeat the task multiple times, for example 1000 times. Okay, so 800 times it will say right answer. Okay, then that is the highest probability. Then with interference, that is constructive interference, so you are increasing the probability of the right answer. With destructive interference, you are decreasing the probability of wrong answer. So that's how it is doing. So I just run it now. Python c naught.py. So 1000 times I run. By default it is 1000. Number of shots for sample is 1000. So answer is 1 1. Okay, now we will again see the code. So here, 1 minute. So this is the code. Here what we are doing, here we are creating 2 qubits. Okay, here we are creating 2 qubits. Okay, because q vector of 2. So for first qubit, that is 0, q0, we are up. This is q1. For first qubit, we are applying NOT gate. Okay, we are applying NOT gate. NOT gate is negation gate. If it is 0, it will be 1. If it is 1, it will be 0. Okay, so here for so we are putting C NOT gate from qubit 0 to qubit 1. This is a C NOT. So that means control NOT. So if the first bit is control bit is 1, then it will do the negation. If it is 0, it will send it as it is. So qubit is initialized basically to 0 only. Okay, basically it is initialized to 0. So both are 0 at the beginning. Okay, because we are not assigning anything. So here not get, so 0 become 1 here. 0 become 1 here. Since the control bit, okay, C naught, control and target. Okay, this is a control qubit, this is a target qubit. So control qubit now it become 1. So control qubit it become 1. So it will negotiate this 0 will become 1 here. Okay, so always the output will be 1 1. Okay, understood? The output is 1 1. Okay, that's what we are getting. If you run this program, output is Python C naught. Always you will get 1 1 only. Output is 1 1. So we are getting 1 1 for 1000 shots. If you run anytime, the output is 1 1. You understood how it is coming? Entanglement is achieved through C naught gate. That means actually that first qubit's output is somewhat connected to this second qubit. That's how entanglement. It's mainly C naught gate. Physically, honestly, I don't know physically how they are doing, but yeah, it is in programmatically it is done through C naught gate. Okay, entanglement with an example. Yeah. So example, okay, for example, we have shoe. For example, we have pair of gloves. Okay, and I'm putting in different boxes. Okay, I'm sending one box to different location. Okay, there is no communication, nothing. And so right gloves and left gloves. Okay, so if I open, okay, I have a red gloves, then definitely I know that the other side it has left gloves. So that is one simple example, but actually it is not like that. Entanglement actually the property remains same actually. Lightning strike. Yeah, actually more parameters are involved, so till now yeah, we don't know. Yeah, but we are in the very initial stage, so utility level problems, actually even companies are asking for that utility level problems. Now even IBM is not allowing us to run small things, at least 100 qubits or some problems only they are allowed, they're encouraging. So lightning strikes and those problems, definitely how many parameters you are taking in, so all these things matter. So how you are representing that in terms of qubit, so many things are there. Yeah, Qiskit or CUDA cube. You can try for yeah, because both have a lot of materials, and NVIDIA also has good advantage because it is already well established in the HPC segment. NVIDIA, CUDA, parallel computing, these are already established. When they patch this CUDA Q, and they are claiming that CUDA Q will work in the QPU also. So if it works, then this is the ready to go for solution, because other things only they are focusing on quantum, but integrating with HPC will be hard for them. But for NVIDIA, it is very easy for integrating. So NVIDIA or Qiskit will be good. There are a lot of materials for reference. Books are not needed. CUDA Q, I will just for CUDA Q, GitHub is there, and Qiskit also a lot of materials are available. CUDA Q Academy is also there. CUDA Q Academy is there. CUDA Q GitHub is there. Yeah, many things you can do with GoLab also, But sometimes GPU access, they in GoLab they are not giving GPU access. If you are a paid customer, then they are giving. Yeah, better to go with Linux, Ubuntu, or anything Linux, because most of the things CUDA-Q and most of the things won't work in Windows. Better to go with Linux. Okay. um, yeah, for absolute beginners, you go with Qiskit or CUDA-Q. Reference books concept you can read, but even this GitHub's materials are very simple, very simplified materials. There are a lot of books available, but because this one books may not get updated, you have to wait for the next edition. But this GitHub pages, na, everything they are updating, they are giving Jupyter notebook files, so you can try hands on. So very easy step they are giving, so you can follow up easily. Yeah, yeah. I will give the, yeah, mail ID. I will give. Okay, how to establish HPC in computer lab? So, for example, in computer lab, if you want to make a HPC, all the computers are in the same network. Okay, for to make a HPC, okay, you need a computer, you need a network, you need a storage. So you make one node, one master node, and others is a compute node. In one master node, you should have two network interface card. That means two LAN card you should have. One LAN card for internal connection and one LAN card for external connection. So master node should have two RJ45 connection. Okay, that is the only requirement. After that, you should have one common space, because everybody is going to write and read in the same space. No? So you should have common space, either NFS partition or something. Okay, you can create a NFS partition, you can mount it in all the compute nodes. So common storage is done. Okay, two network interface card for master node is done. Then you need MPI communication. MPI software has to be installed. Then all node to node communication should happen without passwordless authentication, that is through public key encryption. Okay, public key, private key, RSA key. You have to copy it, so that key based it should go. Okay, node to node communication should go without passwordless authentication. So mainly it is three four things. Okay. um okay, I'm just writing. Master node should have two interface, um, common storage, third is passwordless authentication with RSA key, public key. Okay, public key, private key. So these are then MPI directives. MPI. These things are needed to set up the lab. Linux is always better for HPC. Okay, CUDA-Q. We can say it is the only option actually. Windows is not the option. Yeah. Yeah. Python, C++, but Qiskit actually, in future, I think they are going for Rust programming, because Python will slow the system. It is easy, but it will slow the system. So people are changing to C. Always C has more advantage in terms of performance, but for easy learning curve, Python is easy. Not at all. For CUDA-Q, you can run in CPU also. GPU is not necessary. You can run in CPU also. I will show you. better to go with Linux. Better to have some good GPU card and concentrate on CUDA programming. There are very less experts in CUDA itself. So CUDA itself has more value. Yeah, GoLab you can run. No issue. Linux is always better. This example, everything, CUDA Q Academy is there. CUDA Q Academy is there. So there actually you will get all Jupyter Notebook with explanation, very good explanation. So you can follow this also. Yeah. Okay. So I have some other programs. So this is GHZ. Okay, I will just go through the slide for some time. Okay. So curse of dimensionality, I will show you. Okay. So if you make what is Bell state is 2-qubit entanglement is called Bell state. Okay. So if you want a many qubit entanglement, that is called Greenberger Orny Zeilinger state. Okay. GHZ state. I will just show you simply this one. Okay, I am just running this program. Which is it? So it is 3-qubit. Okay, so all three is 0 or 1. That means fully entangled state. So it is run. It is run for 1,000 steps. 527 times I am getting all 0. 470 times I am getting all. So if I put 4-qubit. Okay, so 4 zeros and 4 1. If I put 9. So 9 zeros and 9 1. Okay, if you can count it, you will get it. Okay, 9 zeros and 9. So similarly, I am just putting 30. So 30 zeros and 30 ones. 521 times zeros and 477. So we are not getting, for example, okay, 2 power 30 is what? So very big number. Okay, so for example 2 power 4, so 2 power 4 is 16, so I should get 16, but instead of 16 possible states I am getting only 2 state, all 0 or all 1. I'm not getting anything in between states. I'm not getting 0001, I'm not getting 0100, I'm not getting 1100, because this is fully entangled state. Okay, so multi-qubit entanglement. So 31 I am putting. So okay, so we are getting 2 states only, fully entangled 2 states only we are getting. 32 we are getting error because 32 we are getting error because 32 we are getting error because the runtime error requires size is too big. When you jump from 31 to 32 is not an error in your code, but the fundamental limitation of the classical quantum simulator. Instead of powering GPU accelerator once like CUDA Q NVIDIA target, so this is not the error. So memory is exhausted. Okay, so for one floating point 64 bits double precision, so 16 byte is needed. So 2 power 31 is into 8 byte, this is 16 GB, this is 2 power 32 need 32 GB, but my GPU has 24 GB RAM only. This is 24 GB RAM. Okay. Yeah, this is 24 GB RAM. This NVIDIA A30 has 24 GB RAM. That's why I am not able to run 2 power 32. Okay. This is the curse of dimensionality. So for okay, 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 I will run another program. Just variable quantum eigensolver. So what is eigenvalue? What is eigenvector? What is Hamiltonian? So Hamiltonian is the total energy of the molecule or okay, total energy means it's a potential energy plus kinetic energy. So all the system want to come to the stable state, that is ground state, okay, equilibrium. So always it's very hard problem to find the lowest energy, okay. So that's why this variational quantum eigensolvers are coming, okay. So we are actually in the code, um, we are creating the angle, okay. We have a particle, okay, subatomic particle. We are just spinning the particle with some angles, and we are finding the energy of it. Hamiltonian is energy, okay. If it is in the zero, it is the highest energy. If it is in this angle, if you twist this, the energy is calculated. If you twist in this degree, the angle is the energy is calculated. If twist, so like that 20 samples have been taken and energy is calculated. Out of that, we have to find out which is the lowest energy, okay. So I just have another program, VQU2. So in this angle, the lowest energy is achieved, okay, for this some program, okay. So why lowest energy is needed? I will just, okay. Yeah, every physical system, okay. Every physical system naturally moves towards the lowest possible energy state called the ground state. Okay, I want to tell one analogy here. I don't know whether it is relevant or not. For example, our saints, they will go to some mountain, okay, glaciers or something, and they will do meditation. Okay, so what they will do, they will not do anything. Okay, they absolute silent. They want to be in absolute silent. Why they are in absolute silent? Because they are trying to find their lowest energy, minimum energy, ground state. They want to analyze their ground state. Why ground state? Why they have to find out their ground state? Because if you know the ground state only, lowest energy only, then you can understand that material better, okay. That's why ground state is needed. If you understand it better, then you can utilize it better, okay. So most of the scientific problems are, every physical system naturally moves towards the lower possible energy state called the ground state. A ball rolls down, stops at the lower point. A molecule electrons rearrange to minimize total energy. A magnet spins aligned to minimize magnet energy. Why ground state energy matter? Molecules determine bond strength, stability, and reaction energy. For that, we need ground state. Material determine conductivity, magnetism, and phase transition. We need to measure the ground state. An atom define the electron configuration, spectra, ionization energy. We need ground state. So for most of the things, we should, to understand it better, it can be understood in the ground state only. So that's why this variable quantum eigensolver and quantum phase estimators are so critical. They find E of 0, that is lowest energy, with classical method struggles to compute for complex molecules. Even HPC struggles to compute. Among all eigenstates, eigenstate is, okay, each state has different energy, okay. Which state has lowest energy? That is the stable state, okay. Okay, I think yeah, yeah, I'm done. So any doubts, any questions?
Participants, if you are having any doubt, you can ask, as Sar has already answered all the questions, I think.
Julia is also good. HPC people are using Julia. Julia also good. But if you are learning now, you can go for Rust.
Sir, I think participants are also not having any doubts, so I think we can conclude the session here.
Okay, okay, yeah.
So thank you so much, sir, for the wonderful session.
Thank
The
you.
session
Thank
is
you.
very informative.
Thank you. Thank you.
So participants will.
Yeah, Madam, this is from APSCHE, Dr. Anil Kumar. Sir, there is
Yes,
lot of positive feedback on you. They want more from you. This is the participants' feedback.
Okay, okay. Thank you, thank you.
I have had some experience. Thank you very much, sir. Thank you.
Thank you, sir. Thank you.
Madam, yes, you close this.
Okay, okay. I will disconnect. Yeah. Thank you, sir.
thank you, sir. Thank you, sir.